Okay, welcome to Chapter 16, Section 1 on Sound. Let's get right to the key ideas here. What are the characteristics of sound waves? How do musical instruments make sound? How do ears help humans hear sound waves? How are the reflection of sound waves used? So, let's start out with properties of sound. What are the characteristics of sound waves? Sound waves are caused by vibrations and carry energy through a medium. A sound wave, basically defined, is a longitudinal wave that is caused by vibrations, and that travels through a material medium. In air, sound waves spread out in all directions away from the source. Speed of sound depends on the medium or the material through which the sound is traveling. So the speed of sound in a particular medium or material depends on how well the particles can transmit the motion of sound waves. Sound waves travel faster through liquids and solids than through gases. Speed of sound in various mediums. As you can see here, the speed of sound in air is fairly low, 331 meters per second at 0 degrees, at 25 degrees C, 346, at 100 degrees, 386. Then you go on up to water, is up to almost 1500 meters per second, which is almost 5 times the speed of sound in air. And then you go into some solids. You go up to like iron. Speed of sound travels in iron at 5,000 meters per second. So a very fast speed through denser materials. Here that you have water, copper, iron, all those are very dense materials where the particles are packed very closely together, so they're able to transmit those energy waves through to the other particles located close by them very quickly. So sound travels. In air, the particles are spread apart. It's a gas, so the particles are spread apart and have a harder time interacting, so the speed doesn't travel as fast in those. Alright, let's listen to this little audio here.
Speed of sound. A sound wave is a longitudinal wave caused by vibrations that travel through a material medium, such as air, water, wood, or glass. Sound travels at different speeds depending on the material through which it is moving.
Okay, so let's move on here. Loudness of the sound is something determined by intensity. So loudness depends partly on the energy contained in the sound wave, and intensity just describes the rate at which a sound wave transmits energy through a given area of a medium. And intensity depends on the amplitude of the sound wave. As you remember I was talking about in the previous chapter, amplitude is the more amplitude, the more energy a wave is carrying. Your distance from the source, because it goes out, it spreads out spherically. So as it spreads out, it loses its energy. The greater the intensity of a sound, the louder the sound will seem. Alright.
Sound intensity and decibel level. The amplitude of a sound wave determines its loudness. The larger the amplitude is, the louder the sound. The human ear cannot detect all possible intensities of sound and does not perceive a doubling of the amplitude as a doubling of loudness. To relate the amplitude of sound waves to human perception of sound, we use relative units called decibels.
Okay, so the decibel level gives you an idea of the sound level of different sounds. So softest sounds are around the 0 decibel level. There are sounds that are smaller than that we just can't interpret. So something like a normal conversation gets up to around 60 decibels. You get up to like a loud rock concert at 115 decibels. Threshold of pain is 120 decibels. That's a real intense, very large amplitude of wave there, which will move your eardrum quite intensely. That's why you have pain associated with it. Then you have jet engines and rocket engines, which are extremely loud objects. Okay, we have something called pitch. Pitch is determined by the frequency of the sound, whereas the amplitude determines the loudness. And a pitch is a measure of how high or how low a sound is perceived to be depending upon the frequency of the sound wave. We talked a little bit about that when we were discussing the Doppler effect. A high-pitched sound corresponds to high frequency or a lot of waves, and a low-pitched sound corresponds to a very low frequency or not very many waves hitting you per second. So let's look at this video on pitch.
The frequency of a sound wave is the number of waves produced each second. A high-frequency sound source produces more sound waves each second than a low-frequency sound source. Pitch refers to human perception of the sound produced by a sound wave. We say a sound is high-pitched or low-pitched, and we refer to musical notes as being a certain pitch. Tuning forks provide a standard for the correct pitch of musical notes, so they are good examples to show how the pitch of a sound depends on the frequency of the sound wave producing it.
So, humans hear sound waves in limited frequency ranges. So any sound with a frequency below the range of human hearing is known as infrasound. Infrasounds are slow vibrations of frequency lower than 20 Hz or lower than 20 cycles per second. And any sound with a frequency above human hearing range is known as an ultrasound. Ultrasounds are any sound waves with frequencies higher than 20,000 Hz. So let's look at comparing infrasonic and ultrasonic waves.
Sound waves that the average human ear can hear are called audible sound waves. Audible sound waves have frequencies between 20 and 20,000 Hz. Sound waves with frequencies less than 20 Hz are called infrasonic waves. Sound waves with frequencies greater than 20,000 Hz are called ultrasonic waves. Some whale songs are infrasonic. Blue whales, for example, produce songs as low as 2 Hz. For a human to be able to hear this song, it would have to be speeded up 10 times. By the same token, bats commonly use ultrasonic sound in the range of 20,000 to 80,000 Hz for navigation.
Alright, musical instruments. So how do musical instruments make sound? Most musical instruments produce sound through the vibration of strings, air columns, or membranes. Musical instruments rely on standing waves that we talked about in our last chapter, and standing waves can exist only at certain wavelengths on a string. So the primary standing wave on a vibrating string has a wavelength that is twice the length of a string. So the frequency of this wave is called the fundamental frequency. So let's watch on fundamental frequency.
On a given string of length L, standing waves exist only at certain wavelengths and frequencies. The lowest frequency at which a string can vibrate, called the fundamental frequency, is determined by the fact that the string is held fixed at its ends. The fundamental frequency of a vibrating string is produced by a standing wave that has a wavelength twice the length of the string, as shown here. Other standing waves that can be supported are simply integer multiples of the fundamental frequency. The sound of an instrument, such as a violin, is due to many of these frequencies being present when a note is played.
So instruments use something also called resonance to amplify sounds. And resonance is a phenomenon that occurs when two objects naturally vibrate at the same frequency. So natural frequencies are specific frequencies at which an object is most likely to vibrate. The natural frequency of an object depends on the object's shape, its size, its mass, and the material from which the object's made. So let's look at resonance here.
Vibration of one object can cause another object nearby to vibrate as well. If the second object can vibrate at the same natural frequency as the first, large vibrations will occur in the second object. This phenomenon is an example of resonance. Resonance occurring between a vibrating tuning fork and a guitar string is greatest when the frequency of the sound wave produced by the tuning fork is the same as the fundamental frequency or lowest frequency of the guitar string.
Alright, so how do ears help humans hear sound waves? The human ear is a sensitive organ that senses vibrations in the air amplifies them, and then transmits those signals to the brain. So vibrations pass through three regions in the ear. Those are the outer, middle, and inner ear. Resonance occurs in the inner ear. A wave of a particular frequency causes a specific part of the basilar membrane to vibrate. Hair cells near the part of the membrane that vibrates then stimulate nerve fibers that send an impulse to the brain. So here you see a depiction of, you've got the outer ear, which is the ear canal, going into your eardrum. So in the middle ear, here vibrations cause the stirrup bone to strike the outer membrane of the inner ear. So there's this little bone here that's connected. You have the hammer and anvil. So this vibrates from the sounds coming in. It transverts it to the inner ear, and inside the inner ear there are hairs that move, and those hairs will send electrical signals to your brain to interpret the sound. Ultrasound and sonar. So how are the reflections of sound waves used? Reflected sound waves are used to determine distances and to create images. Some ultrasound waves are reflected at boundaries. Ultrasound imaging is used in medicine. The echoes of very high frequency ultrasound waves between 1 million and 15 million hertz are used to produce computerized image called sonograms. Some ultrasound waves are reflected back at boundaries. Some sound waves are reflected when they pass from one type of material to another. And how much a sound is reflected depends on the density of the materials at each boundary. The reflected wave can be made into a computer image called a sonogram, which is the image you see if you have an ultrasound during a pregnancy, or if you've seen one of those. Sonar is used to locate objects underwater. Sonar basically means sound navigation and ranging. It's a system that uses acoustic signals and echo returns to determine the location of objects or to communicate. A sonar system determines distance by measuring the time it takes for sound waves to be reflected back from a circuit. So it goes on the old equation we used to use for speed, which is v is equal to d over t, and then just solves it for distance, and that's equal to the speed times the time. And so if you know the speed in water and you can calculate, you send out a signal and use a stopwatch to measure the time it takes that signal to return to you, that sonar signal, then you can calculate the distance that that object is. So let's look here at a visualization on sonar.
Sonar stands for Sound Navigation and Ranging. People use sonar to find objects underwater such as icebergs, formations on the sea floor, and fish. As ultrasonic waves are sent out from a source, they hit objects in their pathway, like this fish. The waves reflect off the fish and bounce back toward their source. The deeper the fish is, the longer the wave takes to reach the fish and then return to the boat. It is possible to calculate the distance from the boat to the fish by multiplying half the travel time of the wave by the speed of sound in water, which is about 15